This is an example of calculating various things whenever we have a situation where we have what we call a locked-in polarization. So think of, putting some crystal in an electric field and inducing some polarization in this crystal here. This is a cylinder-shaped crystal, and so think like a piece of quartz that's milled into a cylinder. You then freeze in somehow the polarization, you turn the external electric field off. And so you have a polarization that is in the material but is not in the external field or anything. And there are three things that we're going to look at. We're going to find the bound charge density, and so this is a volume charge density, that's rho sub b, and a surface charge density, sigma sub b. We're going to find, here I want to think about this as an infinite cylinder, and so this is going off in both directions. I want to find the dipole moment per unit length of this infinite cylinder, and then I want to sketch the electric field for this situation. So down here is a picture of where we will sketch the electric field. First, to start out, I just want to write what this polarization field is. So this polarization field, which is capital P, it's a field, so it's a function that depends upon R, is either P naught, which is just a vector for s less than a, so let's define the size of our cylinder as a, and let's do in cylindrical coordinates here. At least for now we'll do cylindrical coordinates. And then 0 otherwise. Okay, and so this is the functional form of the polarization field in this situation. In order to find the charge densities, we're just going to use the formulas that we have for finding charge density. What we found by doing that neat little trick with the potential where we did the integration by parts is we found that the volume charge density, rho sub b, was equal to minus the divergence of the polarization, and that we found that the surface charge density, sigma sub b, is n hat dot polarization vector, where n hat is the normal to the surface that we're looking at. So we can go ahead and do both of those to start out, and so I'm going to only work in this half of the paper in order to have this hat to sketch the electric field. To start out, we have a divergence of a polarization, but if the polarization is constant or constant in our two different regions, we're simply going to find that rho b is equal to 0 everywhere. Okay. Sigma b is a little more interesting for us. If we make our coordinate system here, okay, we put the axis in the center and call this the x-axis and this the y-axis, so that the z is coming out of the board towards us, so the z is along the axis of the thing. Then the n hat vector, okay, will be in this direction, this n hat vector, and we're going to define this angle as phi. And so I'm able to write down n hat in this case is going to be the x component I hat times cosine phi plus the y component j hat times sine phi. Notice also in this case that this p naught is simply equal to a magnitude p naught times j hat, the way I've got it drawn out here. Taking these two together, this n hat dot p, this sigma sub b, is going to be is now a function of this phi, and it is simply p naught times sine phi, which is kind of interesting. And so it's 0 at phi equals 0, so it's 0 here. It is a positive number up here. It's 0 here at pi, and then it's a negative number here at 3 pi over 2. And so if we were to draw that in, we're going to get a maximum, a lot of positives, right? Here, a few less positives along the sides and nothing in the center. And same down here on the other end with the negatives. We're going to get minus, minus, kind of dense, not positives, dense minuses, and then less dense minuses, and then it's going to go to 0 at those 2 points. And so that's that. So we've answered the question of what the charge density, the surface charge density, and volume charge density are for this situation. So that was part A. For part B, we want to find the dipole moment per unit charge. The dipole moment, all we have to remember is what the definition of our polarization is. The definition of our polarization is dipole moment per unit volume. So the total dipole moment is going to be simply d3x times p naught of r. But we simply have p of r, our polarization, is a constant in this volume, so this is simply going to be equal to p naught times the volume of the thing that we're looking at, which will be pi a squared times the length that we're looking at. So pi little a squared times the length. And so turning that around, we can find that the dipole moment per unit length is p naught pi a squared. And in this case, I forgot to write out that this p naught is a vector. Okay, and so that's it. That's as simple as we have to do. And so this was part B. For part C, I want to sketch the electric field due to this induced polarization. Well, electric field lines start at pluses and go to minuses. And so if I just look here, I'm going to get on the inside, the electric field is going to flow in the opposite direction of the polarization. So the electric field due to the polarization on the inside flows in the opposite direction of the polarization. Kind of an interesting but always true result. And then in the outside here, I'm just going to connect the positive to the negative charges. And so I'm going to do that in kind of the most natural way possible. Okay, and we see something hopefully unsurprising to you, that this looks like a dipole field, and that came around because that's what the polarization density is. If I have a constant polarization, the electric field exterior to that should look like a dipole field, because if you integrate over it, you're going to get a dipole moment. And that's it. This is how you can interpret problems that have locked in polarizations.